Imagine you're on a plane when the engine explodes. This actually happened on November 4, 2010. Qantas Flight 32 had 469 people on board when their Rolls-Royce engine blew apart just after takeoff. This engine was supposed to be nearly indestructible, but it wasn't. And what really happened is more shocking than you think. Let's dive in. At number 7, let's talk about the moment everything went wrong. Number 7. The day disaster struck. Qantas Flight 32. November 4, 2010, Singapore Changi Airport. Captain Richard de Crespigny, a veteran pilot with over 35 years of experience, was preparing for what should have been a routine 7-hour flight to Sydney. Behind him sat 469 souls, passengers ranging from families heading home to business travelers crossing the Pacific. The aircraft was Qantas's pride and joy, a massive Airbus A380, registration VH-OQA, nicknamed Nancy Bird Walton. At 560 tons fully loaded, it was essentially a flying apartment building powered by 4 Rolls-Royce Trent 900 engines, each generating 70,000 pounds of thrust. Everything seemed normal during taxi and takeoff. The engines hummed with their familiar deep rumble. Passengers were settling in for the long journey ahead. But just 4 minutes after wheels up, at 7,000 feet, engine number 2, the inboard engine on the left wing, decided to tear itself apart. The explosion was catastrophic. Witnesses on the ground described it as a massive bang, followed by a shower of metal debris raining down on Batam Island, Indonesia. Inside the cabin, passengers heard what sounded like a gunshot, followed by violent shaking and the acrid smell of smoke. But here's what makes this incident truly terrifying. This wasn't just an engine failure. The exploding Trent 900 had damaged critical aircraft systems. Fuel lines were severed, electrical systems were compromised, the wing structure itself was damaged by flying debris from the disintegrating engine. Captain de Crespigny found himself facing a nightmare scenario that no pilot had ever trained for. His flight management computer was displaying 54 separate error messages. Systems that should never fail were failing, and he had 469 lives depending on his next decisions. The crew made the call to return to Singapore immediately. What followed was one of the most skillful pieces of airmanship in aviation history. But we'll get to that in a moment. First, we need to understand what exactly went wrong inside that Rolls-Royce Trent 900 engine. At number 6, let's talk about the engineering nightmare that unfolded inside engine number 2. Number 6. What exactly went wrong in that engine? The Rolls-Royce Trent 900 is a masterpiece of engineering, or at least it was supposed to be. These engines are marvels of modern technology, with turbine blades spinning at over 10,000 RPM, while containing pressures equivalent to 40 atmospheres and temperatures exceeding 1,500 degrees Celsius. Each engine costs over $25 million and takes months to build. But on that November morning, a single component failure triggered a cascade of destruction that nearly brought down the world's largest passenger aircraft. The culprit was something called an intermediate pressure turbine disc, essentially a massive metal wheel with turbine blades attached, spinning at incredible speeds deep inside the engine. This particular disc had a manufacturing defect, a tiny fatigue crack in the bore of the disc hub. Now, here's where it gets technical but crucial to understand. Turbine discs are forged from specialized nickel-based superalloys and undergo rigorous quality control. They're designed to withstand enormous centrifugal forces. We're talking about forces that would rip apart ordinary steel like tissue paper. But this disc had what investigators later called a manufacturing anomaly, a stub pipe that had been improperly machined during production. The defect created a stress concentration point that, over time, developed into a fatigue crack. Every time the engine spun up, that crack grew a little bit larger. After 3,615 engine cycles, the crack had grown large enough to cause catastrophic failure. The disc literally exploded, sending razor-sharp metal fragments flying through the engine at supersonic speeds. These fragments punctured the engine casing, severed fuel lines, and damaged the aircraft's wing structure. But here's the truly shocking part. Rolls-Royce knew about potential issues with this manufacturing process. Internal quality control documents later revealed that the company had identified problems with their machining procedures, but hadn't implemented comprehensive fixes across their entire production line. The investigation would eventually reveal that multiple Trent 900 engines in service worldwide had similar defects. They were essentially ticking time bombs waiting to explode. At number 5, let's talk about how 4 pilots saved 469 lives through pure skill and teamwork. Number 5. The crew's incredible response. When engine number 2 exploded, Captain Richard de Crespigny wasn't just dealing with a simple engine failure. The cascading damage had created what aviation experts call a multiple systems failure, a scenario so complex that it had never been properly simulated in training. The flight deck was chaos. Warning bells were ringing continuously. The primary flight display showed 54 different error messages, with more appearing every second. Systems that should have been independent were failing together because of the engine debris damage. But here's what makes this story remarkable. De Crespigny didn't panic, neither did his crew. Instead, they did something that probably saved everyone's lives. They slowed down and thought systematically. First Officer Matt Hicks took control of the aircraft, while Captain de Crespigny assessed the situation. Second Officer Mark Johnson began working through emergency checklists, while Senior Check Captain David Evans coordinated with air traffic control and cabin crew. The problems were staggering. The left wing was losing fuel from severed lines. The landing gear was damaged and might not extend properly. Multiple hydraulic systems were compromised. Even the aircraft's flight envelope protection systems, the computers that prevent pilots from accidentally stalling or overstressing the aircraft, were degraded. Most terrifying of all, they discovered that the normal landing procedures wouldn't work. The damaged systems meant they couldn't configure the aircraft for a standard approach. They would have to essentially invent new procedures on the spot. De Crespigny made a crucial decision. They would stay airborne for nearly 2 hours, burning off fuel while the crew worked through every system failure. This wasn't about being cautious, it was about being smart. They needed time to understand their damaged aircraft before attempting a landing. The crew coordination was flawless. Each pilot had specific responsibilities, and they communicated constantly. They tested systems, ran calculations, and prepared for multiple contingencies. Meanwhile, the cabin crew kept 440 passengers calm without revealing the true severity of their situation. When they finally approached Singapore for landing, they were dealing with an aircraft that was barely controllable. The landing would require perfect timing, perfect coordination, and more than a little luck. But we'll get to that dramatic conclusion in a moment. First, we need to understand what investigators discovered when they examined the wreckage. At number 4, let's talk about what investigators found when they dug into the real causes of this disaster. Number 4. The investigation uncovers frightening truths. The investigation into QF-32 was led by the Australian Transport Safety Bureau, with participation from authorities in Singapore, France, and the UK. What they discovered was far more disturbing than a simple manufacturing defect. The shattered remains of the intermediate pressure turbine disc told a story of systematic quality control failures. Metallurgical analysis revealed that the fatigue crack had originated from a manufacturing defect in the stub pipe, a component that connects the disc to the oil system. But here's the shocking part. This wasn't an isolated incident. Investigators discovered that Rolls-Royce had been aware of manufacturing inconsistencies in their Trent 900 production line for months before the QF-32 incident. Internal company documents obtained through the investigation showed that Rolls-Royce engineers had identified problems with their counter-boring process, the machining technique used to create the stub pipe. Some engines had been manufactured with thinner walls than specified, creating stress concentration points that could lead to fatigue cracking. The investigation revealed that Rolls-Royce had issued service bulletins recommending enhanced inspections, but these were classified as advisory rather than mandatory. Airlines weren't required to implement the inspections immediately, and some, including Qantas, hadn't yet performed them on all their engines. Even more troubling, the investigation found that similar defects existed in multiple Trent 900 engines worldwide. After the QF-32 incident, emergency inspections of the global Trent 900 fleet revealed that dozens of engines had similar manufacturing anomalies. The European Aviation Safety Agency immediately issued an emergency airworthiness directive, effectively grounding portions of the A380 fleet until engines could be inspected and repaired. This wasn't just about one defective engine, it was about a systemic manufacturing problem that had put hundreds of aircraft at risk. But the investigation uncovered something even more concerning. The engine's certification process may have been inadequate. The original testing hadn't fully simulated the type of failure that occurred on QF-32, particularly the way debris from one part of the engine could damage other systems. At number 3, let's talk about how one of the world's most prestigious aerospace companies got it so wrong. Number 3. Rolls-Royce's engineering flaws exposed. Rolls-Royce has been building aircraft engines for over a century. Their name is synonymous with precision, reliability, and engineering excellence. The company that gave us the Merlin engine that powered the Spitfire, the Conway that launched the jet age, and the RB211 that revolutionized wide-body aviation. So how did they produce an engine with such a fundamental flaw? The answer lies in the complex manufacturing process for modern jet engines. The Trent 900's intermediate pressure turbine disc is forged from a nickel-based superalloy called Inconel 718. This material can withstand extreme temperatures and stresses, but it's also notoriously difficult to machine. The critical stub pipe, the component that failed on QF-32, is created through a process called counterboring. This involves drilling a precise hole into the disc and then machining it to exact specifications. The wall thickness must be perfect. Too thick and the disc is overweight. Too thin and it becomes vulnerable to fatigue cracking. Internal Rolls-Royce documents revealed that their manufacturing quality control had identified variations in this process. Some discs were being produced with wall thicknesses at the lower end of the acceptable range. While technically within specifications, these thinner walls created stress concentration points that could lead to premature fatigue. The investigation found that Rolls-Royce engineers had recognized this issue and had developed improved manufacturing procedures. However, these improvements weren't implemented across the entire production line immediately. Cost considerations and production schedules meant that engines with the older, less reliable manufacturing were still being delivered to customers. Even more damning, the investigation revealed that Rolls-Royce's own failure analysis had predicted that engines with these manufacturing variations might experience fatigue cracking within 20,000 flight cycles. The engine that failed on QF-32 had only 3,615 cycles. This wasn't just a manufacturing defect, it was a failure of engineering process. The company had identified a potential problem but hadn't taken adequate steps to prevent it from reaching service. At number 2, let's talk about how the aviation industry responded to this wake-up call. Number 2, how the industry reacted. The QF-32 incident sent shockwaves through the global aviation community. Within hours of the emergency landing, European and Australian aviation authorities issued emergency directives affecting the entire A380 fleet. Airlines around the world were forced to ground aircraft pending engine inspections. Singapore Airlines, Lufthansa, and Air France immediately suspended A380 operations. The financial impact was enormous. Each A380 generates millions of dollars in revenue, and suddenly dozens of these aircraft were sitting on the ground. But the industry's response went far beyond immediate safety measures. The incident exposed fundamental weaknesses in how modern aircraft systems are designed to handle catastrophic failures. Traditional aviation safety philosophy relies on redundancy. If one system fails, there's always a backup. But QF-32 demonstrated that a single engine failure could cascade into multiple system failures when debris damages other components. This challenged decades of safety assumptions. Aircraft manufacturers began redesigning engine containment systems. The traditional approach assumed that a failed engine would contain its debris within the engine casing, but the Trent 900 failure showed that high-energy debris could punch through containment systems and damage other aircraft systems. Engine manufacturers implemented new quality control procedures. The entire industry adopted more rigorous manufacturing standards and enhanced inspection protocols. The goal was to prevent manufacturing defects from reaching service aircraft. Pilot training programs were overhauled. The complexity of modern aircraft systems meant that pilots needed better preparation for handling multiple simultaneous failures. Simulator training scenarios were updated to include more realistic failure modes. The changes weren't just technical, they were cultural. The industry acknowledged that the rapid pace of technological development had outpaced some safety practices. There was a renewed emphasis on understanding failure modes and ensuring that safety systems could handle unexpected scenarios. At number 1, let's talk about why this 14-year-old incident is still relevant every time we board an aircraft. Number 1. Why this matters for every flight today. The QF-32 incident fundamentally changed how we think about aviation safety. It exposed the hidden vulnerabilities in our most advanced aircraft and reminded us that even the most sophisticated engineering can fail in unexpected ways. Today, every commercial flight benefits from lessons learned from that terrifying day in 2010. Engine manufacturing processes are more rigorous. Quality control procedures are more comprehensive. Pilot training is more realistic. Aircraft systems are designed with better failure tolerance. But the incident also revealed something more profound about modern aviation. Our aircraft have become so complex that understanding all their failure modes is nearly impossible. The Airbus A380 has over 4 million components. The Trent 900 engine alone has over 25,000 parts. When these systems fail, they can fail in ways that nobody anticipated. This is why the human element, the skill of pilots like Captain de Crespigny and his crew, remains crucial. No amount of automation can replace the judgment, experience, and problem-solving ability of skilled professionals when everything goes wrong. The QF-32 incident also highlighted the importance of transparency in aviation safety. The investigation's findings were shared globally, allowing every airline and manufacturer to learn from Qantas's experience. This culture of open information sharing is what makes commercial aviation as safe as it is today. A tiny defect caused a massive engine to explode. The crew saved 469 lives. The investigation revealed shocking problems. This changed aviation forever. Every flight today is safer because of what happened that day. What do you think? Let us know in the comments. Subscribe for more aviation stories. Thanks for watching.